Okay, welcome to the electrocardiogram. This is the EKG1 PowerPoint. So the big thing I want you to start with is the definitions over here. So an ECG or an EKG is just representing the electrical activity of the heart. So what we're doing is we're trying to look at an acute condition that would suggest there's heart disease going on. So sometimes we'll do an EKG and there's no condition that's showing up on the EKG, but it's showing up in their lab. So someone comes into the hospital with chest pain, we're still going to do an EKG or an ECG, and it may be a myocardial infarction. It might be a heart attack and just not showing up yet on the EKG, but it may show up on the lab. So that's something that we might see in their troponin levels. So that's why it's also important to understand the lab values as well as things like the EKGs when you're looking at heart disease and myocardial heart disease. The big advantages is the EKG is quick, it's inexpensive, it's non-invasive, and it shows conduction of the heart. So we can see how weak or how strong the conduction is, or if there's something abnormal with the conduction activity of the heart. The big disadvantages is it cannot predict future problems. It only shows what has already occurred. It won't show, it's not a looking glass. It won't show future problems. It only shows what has only occurred currently. So we're only looking at the electrical activity. It doesn't give us any real definition or any real thing beyond that. The heart cells, the myocardial working cells, there's two types. There's the specialized pacemaker cells, the myocardial working cells. The myocardial working cells create the physical contraction, the squeeze of the heart. The specialized pacemaker cells, they control the rate and the rhythm. So myocardial working cells create physical contraction of the heart. The pacemaker cells control the rate and the rhythm. So those are the two primary cells that you're going to be looking at. So when we're looking at the electrolytes and cardiac function, they're very important. And this is why understanding if a patient has very poor electrolyte balance, that might affect their heart function as well. So that's one of the things that you'd want to look at on their labs. If their heart was functioning poorly, we'll obviously get an EKG, but we'll also look at their labs as well. That's why it's important that you understand both of what all is going on. So cations and anions are the big things that we're looking at. Cations are important for cardiac function. Your big ones are sodium, potassium, calcium, and magnesium. Your anions, which are negatively charged, the big ones in your cardiac muscle are going to be phosphorus and chloride. So those are going to be your primary cations and anions. When we're looking at polarization, in the resting state, potassium concentration is greater inside the cell. It is greater inside the cell. Sodium concentration is greater outside the cell. So both of those are cations. So potassium is greater inside, sodium is greater outside. Inside the cell is a negative relative to the outside the cell. Because there's larger ions, it makes it more negative. So that's why there's that influx into the cell. Because the inside of the cell is negative, relative to the outside of the cell, that will cause that to flow. So sodium and potassium will exchange through an active method of transport. This is the sodium-potassium exchange pump that you're looking at here. Resting state is the isoelectric line. So the resting state is the isoelectric line. So when we're looking at this, we're looking at that exchange of the sodium-potassium pump. So if someone is hyponatremic or hypokalemic, we're going to have big issues with the pump or the polarization of the myocardium. And so that can make for a lot of issues, obviously, with your patient's condition. When we start to look at depolarization, this is the trigger for myocardial contraction. So sodium ions will diffuse into the cell and reverse its charge from the inside from negative to positive. So this is just changing the polarity inside, and this is phase 0. So the changes of polarity is referred to, they call it action potentials. And so you'll see this in your reading material. This is the change from positive to negative, negative to positive. This is the change of polarity, aka action potential. So we're looking at phase 0 here. In phase 1, this is where potassium flows out of the cell, which produces an early but incomplete repolarization. So this is what you'll see on that graphic there. This is what we're seeing in this that short downward stroke in action for phase 1. It's not quite complete there. When we get to phase 2, you have the slow inward flow of calcium, which slows the outflow of potassium. This is that plateau that you've seen on that action potential from that previous slide. So that calcium will slow potassium from coming out of the cell in phase 2 of repolarization. In phase 3, we're looking at the inward flow of calcium will be stopped, and then potassium will then accelerate out of the cell. This is that big downslope, or phase 3 of that action potential curve that you were looking at on that slide previously. This is what we're looking at for phase 3 of repolarization. Phase 4, the ion channels will return to their depolarization permeability. So this is the baseline, back to the baseline on the action potential curve. This is known as the resting phase. So phase 4, repolarization, is the resting phase. So when we're talking about these things, one of the things that we'll be looking at is refractory periods. So there's an absolute refractory period, and then there's a relative refractory period. So an absolute refractory period is a time which the cells cannot respond to a stimulus. They're already busy doing other things. They cannot respond. So this would be phases 0, 1, 2, 3 in the first half, 0, 1, 2 in the first half of 3. So this is ultimately to the beginning of the QRS complex to the peak of the T wave. So after that T wave, we enter this sort of relative or vulnerable state. But during this QRS complex and the peak of the T wave, they're in an absolute refractory period. There is not the right ion balance to receive stimulation during this period, and that's what makes it an absolute refractory period. When we're looking at relative or vulnerable refractory periods, this is the time which repolarization is almost complete, and strong stimulus could cause depolarization of some cells. So obviously this is going to be the second half of phase 3 if we went to the first half of phase 3 with absolute. So this will be the second half of phase 3, and this is the downslope of the T wave. So when the downslope of the T wave starts, that's when it could respond to some stimulus. It's a relative refractory state, but this is a very vulnerable stage. Some of the depolarization of the cells could occur here. This is that downslope of that T wave. Non-refractory periods, when the cells are in resting or a polarized state, this is what we're looking at during phase 4. So this is that resting stage, this is that refractory period. These cells are ready to respond. This is the isoelectric line I would highlight or write down. This is the isoelectric line. These cells are ready to respond to a stimulus to go into a cardiac electrical activity again. All the refractory periods can be altered by many factors. Some of them are altered by medications, disease, electrolyte imbalances, and myocardial injury. So all these things can alter the refractory periods and make it so it's a long or a slow pattern in between conductions. That would be a bradycardia, or they could speed it up if they were improper and make it a tachycardia. But this are things that can absolutely affect your refractory period: medications, disease, electrolyte imbalances, and myocardial injury. Some definitions: you do need to go and look at your definitions. These are things I would expect you to understand. This is automaticity is the first one. This is the ability to work without stimulation. So these guys have their own way of doing things. They don't get real input from anyone else. This is the ability to work without stimulation. So these are located in the SA node. The SA node is your primary pacemaker. Your backup pacemaker is your AV. And then the Purkinje network is ultimately the last one. That would be more of a ventricular rhythm ultimately when we get down to it. So your automaticity cells are mainly located in your SA, AV, and Purkinje network. As it goes down, the heart rate would slow down. So let's say your SA node's not firing anymore, then your AV node would then take up doing the junction or take up doing the stimulation, and that would be a slower heart rate. And when you get down to the Purkinje network, being the primary pacemaker, if you do lose that backup of the AV and you go to your third backup of the Purkinje network, then that would be an even slower rate. And you would see all these changes on an ECG. The second definition is looking at cardiac excitability. This is where we look at the presence of ischemia and hypoxia that can cause the cells to become excitable. So these are located in all cardiac cells. And these are cells that can respond to stimulus or irritation. So here's the thing with excitability. We can have what's called the supraventricular tachycardia. In other words, the pacemaking of the heart is not done by the SA node. There's external stimulus that's causing irritation on the heart to beat faster, super fast. And so that would be a response to stimulus, or that would be excitability. That would not be automaticity. Conductivity, I know you guys love definitions. Conductivity is the ability to transmit a current from cell to cell. So this is just like that thing where you did when you were a kid where you put two cups in a string together. Yeah, you're looking at conductivity, the ability to transmit a current from cell to cell. This is located in all cardiac cells. They love to talk to each other. So that's that conductivity, the ability to transmit. So the SA fires, then it would transmit to the AV, so on and so forth. This is where the heart muscle is contracting both ventricles and atrias. They're all doing this coordination, this choreography, if you will, all at one time. So that conductivity is the ability to transmit a current from cell to cell. Rhythmicity or contractility, this is located in your myocardial cells. So this is the myocardium, the muscle of the heart itself. This is what causes the cardiac cells to become shortened, which causes the cardiac muscle to contract for systole, right? So this is the cardiac muscles, or the myocardium, and this is where the cells will be shortened to cause that myocardium to contract. Last part of this presentation here is looking at just your review of the conduction system. You should have remembered this and memorized it from first semester here, but we'll go over it again. Remember, your normal conduction system starts at the SA node, then travels to the AV node, to the bundle of His, to the left and right bundle branches, and then finally to the Purkinje fibers. And this is when we're looking at, when we'll look at bundle branch blocks and things like that, you're going to be looking at the different conduction through these different areas. Right, and so this is what you're looking at, where the SA, the AV, the bundle of His, the SA is located in the atrial, the AV is also located in the atria, and then as you get down further, you're going to look at more ventricular rhythms, which is why you'll see different EKG patterns when you start to get into these different types of pacemakers.